Now that we have a better idea of how a double replacement reaction could be possible in water, after taking a look at the particulate diagrams, it's time to be able to better communicate with a bit more exacting preciseness, to be able to write down and communicate exactly what's happening during that double replacement reaction. We need to be able to communicate that in a balanced chemical equation. So let's actually talk about this. When we have a double replacement reaction, it's important to remember that this is between two ionic compounds. So in a general form, we say AB. Now that represents one ionic compound where you have a cation in front, that's A, and B would be the anion in the back. And another compound, C and D, C would be the cation and D would be the anion, positive and negative. And remember that if this is actually a real particulate drawing here, these would be in water, they'd be separated, and then they'd kind of be rotating all around in the solution. But when we have this on paper, there is a little bit more of an easy way to envision this. Now, remember, the generic form essentially has partners switching places. I like to think of this almost like the tushy part of both of these compounds have switched places. So the anion, the B and the D component are just simply going to rotate positions. So notice that B ends up where D was, and D ends up where B was. We just need to make sure that we can write this out beautifully. Let's take a look at a real chemical example. How about the reaction of NaCl meets PbNO3 Now, the first thing that we're going to need is those state symbols. Double replacement reactions require that both of the reactants that are going in are both aqueous. Otherwise, this isn't going to work. Now, remember what aqueous really means. That means that the cation and the anion are no longer attached when they're in water. So I'm actually underneath these two compounds going to write down the formulas and the charges of both the cation and the anion. With some of these compounds, it's a little bit hard to remember how to figure out their charge, particularly with those compounds that contain transition metals, like the lead compound. Remember that in about 99% of cases, you can uncrisscross the subscripts to figure out what the charge of that metal was. You should be doing algebra and confirming that all of these charges do line up, but in this case, a 2 would backtrack back to your lead, giving you a lead 2+ charge. So now all we need to do is to do-si-do our lovely little anions. We're going to have our anions switch positions. So that should create two new pairings. We should have Na1+ paired up with NO3 1-, and we should have Pb2+ paired up with the Cl1-. Now notice, when I had them on my product side, the Na and the Pb did not move positions. They're still in front. It's the tushy part of these two compounds that have switched places. Now I'm all ready to start to finish up my compounds. So the next step would be to write the final finished, beautiful, crisscrossed chemical formulas. So I'm going to crisscross my charges and write my final compound formula, NaNO3. I'm going to crisscross my second charges and write my final compound formula, PbCl2. Now remember your good formula writing. These do need to be in lowest terms possible. So reduce when you possibly can. All right, so now I have at least my compound formulas predicted. The next step is going to be to balance my equation. So underneath each side, I'm going to list what I've got, each ion individually. And I notice right off of the bat that my chlorine ions on my list are not equal on each side. So I'm going to fix it by putting a big coefficient 2 in. And that kind of throws my sodium out of whack. So I think let's fix that with another 2 coefficient on the product side. I'll multiply that in and through. That did bump up my nitrate. Looks like my leads are still good. Everything else looks good. I think this equation is now balanced. One last step before we completely call this a success we're missing state symbols on our product side. We do need to predict those as well. So we'll use our solubility rules. Remember that anytime that you have nitrate, well, that's going to be an AQ compound. And ordinarily on your second compound, Cl, that's part of the halogens. A lot of the times halogens make AQ compounds with very few exceptions. And that one exception right now is when it's with Pb. It's going to form a solid. So I throw my beautiful little state symbols up there, and now I have a finished, perfect, balanced double replacement reaction. We've successfully predicted those products. Now, in this case, this would actually be known as a precipitation reaction because we formed a precipitate. Now, ordinarily, the word precipitation probably brings to your mind weather, rain, snow, sleet, hail, all of those types of things. That's a form of material that's falling from the sky. But in chemistry, a precipitate is a combination of two aqueous solutions that when they combine, they form a solid that falls out of the solution, just like snow would from the sky. And they look beautiful when they're made. Here's a beautiful example. In fact, actually, this example exactly, this is insoluble lead chloride being formed through a chemical reaction. Here are a couple other examples, just absolutely gorgeous when they do form. And then one that you can actually see in action. You can see before the chemical reaction, you're dealing with two perfectly clear solutions. But as we add them together, this insoluble yellow precipitate starts to form. And if you let it sit long enough, that precipitate does in fact fall all the way down to the bottom of the beaker, just like snow would fall back down to the earth. Now, what's really kind of neat is that a precipitation really only occurs if a precipitate is formed. And of course, you're probably saying, no duh, but it only really happens if you're going to form that solid. So one of the products on the product side has to be marked as being solid or being insoluble. Otherwise, if it can't be, then when we add those two reactants together, no reaction is actually going to occur. Let me give you an example of this. Here is a double replacement reaction. Let's practice predicting the products again. Now remember that my first step was to write down the ions and their charges underneath. So I have Na1+, Cl1-, Li1+, and OH1-. All of those easily predictable from the periodic table. Now I'm going to do-si-do the anion portions and write down my two new combinations. So Na is now going to be paired up with OH. Remember to write the positive first, the negative second. And I'm going to have Li now paired up with Cl. Make sure that you crisscross your two new compound formulas. Luckily, since everything is a combination of ones, so will be our subscripts, so those can just disappear. I want to make sure that we're balanced, and luckily this is a very simple equation. It is already balanced. And then the last step, of course, would be then to supply the state symbols. And in this case, both of our products, according to the solubility rules, would be marked as being AQ. In this case, this would indicate no reaction. No chemical reaction actually takes place because before the reaction starts, all of our ions are floating in solution. After the reaction is over, all of the ions are still floating in solution. It's like there was no change. One more example, just to make sure that we really hammer this home. Let's take a look at HCl aqueous reacting with LiOH aqueous. Again, write down the ions and their charges. Do-si-do the anions. Let's start to write down the two new combinations. So H1+ is now paired with OH1-. Li1+ is now paired with Cl. Crisscross your new compound formulas. In this case, since everything's one, they would just simply go away. Now we also want to check to make sure that we're balanced. Luckily, in this case, it's already balanced. And now we're going to need some state symbols. Now, HOH, I know that that looks a little odd as a formula. That really is H2O, water. Now, the state symbol of water is going to be important here. We're going to put him down as liquid. Water cannot dissolve in water. Water is just more water. So his state symbol will always be liquid under normal conditions. And the LiCl, according to the solubility rules, would be AQ. Now, what's very interesting is because we have water forming and because his state symbol is liquid and not AQ, this is a chemical reaction. Remember that in order for one of these double replacement reactions to occur, one of the product state symbols has to be something different than AQ. So in this case, again, H2O, that's not AQ, that's liquid. This is a reaction, and this is very, very typical of your acid-base style double replacement reactions.